for inviting me to participate today. I've been at a few of these, and it's been interesting to watch the kind of community and the community change over the years as HPC is adopted more and more for solving difficult problems. So I'm so lucky that all these presenters came before me, because the one thing that I'm going to focus on is the hard problem that the previous speaker talked about, which is trying to use data science for 3D CFD. I'm going to talk a little bit about our company, and then the big data problem as it relates to CFD, because there are issues and opportunities within that where people can get leverage and get more throughput, more performance, and then how that ties to analytics. So we've been around for 34 years. We predate frame buffers, I like to say. And when we first started to do visualization, you had to write things out to film a scan line at a time. We got involved with fluid dynamics through a project with United Technologies, and we've been in that space ever since. The interesting thing about fluid dynamics is it's nonlinear, it's complicated, it's big, and for people who really need it, it's mission critical. So we thought that was a very interesting area. And we've used both input from customers and so-called SBIR government research contracts to advance our technology over the years. And we've been lucky that NASA and Department of Energy and Department of Defense have thought we've had some good ideas along the way. So we have essentially three parts to our company. Software products, our main product is FieldView, which is pretty dominant worldwide for CFD post-processing. Over the years, we've built into FieldView data management and other types of things I'll talk about a little bit. But when we started to work with Department of Energy, we got involved with more open source type projects. So we also commercialize a version of the Department of Energy's Visit software, which is a highly scalable visualization and data analysis tool. And we just released last week the first combination of those two products, which we call HPC FieldView, which has a FieldView desktop client, and the back end is the fully scalable Visit engine. It's kind of interesting. And what drives our technology is our applied research group. So that's where we get interesting projects. We either propose them or we're approached to do things in uncertainty quantification or different types of risk reduction for data processing. And a lot of things I'll talk about today in data science was actually started for us by an Air Force Research Lab Propulsion Directorate project for gas turbine post-processing. So this is a roadmap of CFD from a different perspective. So NASA paid for a study to see what they think the needs of CFD are going to be for aerospace in 2030. And so they've broken it down into different types of solver technology, and I'm focusing on knowledge extraction because that's what we're about. And when I showed you that initial curve with getting involved with visualization a long time ago, the whole idea was that visualization was the end game. You took data, you did a calculation, then you looked at some movies or pictures, and you tried to then understand what the phenomenon was. And when you start getting into 100 billion point unsteady calculations, and you're running 10 or 100 of those, it's not possible for a human being to process that visual information and understand things. And so over the last 5 years, we've been really trying to figure out how to integrate data science into the interpretation and characterization of complex 3D CFD analysis. I think this is one thing that's funny. 2020, 10 billion point unsteady. Our customer, JAXA in Japan, is doing that with FieldView now. So they're a few years, 2 years ahead, I guess. That's a good point to be on. So a little background on CFD in the engineering process. Why do you do CFD? Well, sometimes you want to understand the physics of a device because you want to make it better, so you want to understand it. You want to test out theories about changes in design. If you want to make a Formula One car go faster, I might want to change the front wing. How's that going to perform? If you make a change, how is that going to do? I don't want to have to build a test airplane if I don't have to. And then the holy grail is the last one there, which is to certify performance by simulation. There's a great goal to reduce the billions of dollars spent on testing airplanes to certify them, and also testing cars by simulation rather than have to do so much physical testing. But in order for all these pieces to come together, the simulation has to be believable and the uncertainty has to be well understood. And the general steps are, you have some CAD or some geometry, you create a discretization, set up the job, compute it on some kind of HPC resource, and then analyze the result. And today, one of the speakers talked about using competitive training to train a neural network to be able to do replace a Markov process. And those simulations were running at 7 seconds apiece. And we typically have simulations, they don't run for less than half a day if they're real. And sometimes simulations will run for 2 weeks. Production simulations are 2 weeks. So if you start thinking about that in terms of data science, it takes a long time to get training data. So that was a very interesting point about Ford and the previous speaker, starting to create training data from everything you calculate. And that's certainly one of the things that we endorse. So if you look at the big picture, right, you're in this cycle of deciding you want to change something, you create the geometry, you evaluate it, you down select changes, and then you evaluate again. Maybe it's a wind tunnel or some kind of test. Then you actually build something, test that, and all during this time, you have in your mind a conceptual system model, right? If I make the wings fatter, this will happen, or if I make the tires wider, this will happen. And one of the things that we're really interested in is, how can machine learning impact the conceptual system model so that you can actually use that to guide which geometry choices are you going to make ahead of time? That seems to be a really interesting chance to leverage machine learning against engineering. So what are the issues, right? Well, because there's always, it's not a perfect world. So results file size is directly related to the precision of the discretization. So, typically 5 gigabytes to 10 gigabytes is an average single steady state run file. They're not small. The HPC resources can be physically or logically distant, meaning that you can't just reach and touch the data, you got to copy it or move it or do something. And then you exacerbate all that by the fact that optimization, uncertainty quantification, and unsteady calculation require many, many files or many runs. So it's not unusual for Boeing to run 1,000 wing calculations as part of an optimization, or 10,000 to position a pylon on a wing. And so what do you do with 10,000 calculations? And how do you digest that data? And making things worse is the fact that that disk storage, even though you can buy it, is not getting any faster. And this is raw disk performance. Forget about the file system on top of it. This is just head on disk kind of stuff, right? That compute over the period from 1980 to now is 10,000 times faster on average in a company. But disk has gotten faster by less than 100x. So there's a convergence of problems. We're actually going backwards. The faster that HPC can generate data, the worse it is to deal with that data. Yet, we want the big data because we want to digest it for machine learning. It's an interesting problem and opportunity. So here's some big data examples. Most of these are old, but I thought they'd be good to show them anyway. This is 45 seconds of simulation at 60 time steps per second. There's a machine flying that helicopter, and the helicopter is actually going through 6 degrees of freedom physics, and it's landing on the back of that ship. And the purpose of this study is to deal with the instabilities that result when that rotor ingests the wake from all the structures that are on that ship. So you see as the helicopter goes down, it ingests the wake. Dirty air means less lift. Things happen to the helicopter. So if you multiply that out, that's over 1,200 files. They're about 10 gigabytes each. And that was computed in Maui, the Maui Supercomputer Center, and post-processed in Washington, D.C. So these these types of unsteady calculations just generate lots and lots and lots of data. And the important thing to notice is that when you get down to post-process and understanding them, what actually makes up the image is a very small amount of the data. And if you're doing, say, an unsteady, rather unstructured grid on a car, and you're doing just drag, say you're doing Formula One or something, you only less than 8% of the data is used to compute the drag. But you have to compute 100% of it for the CFD to converge. So being able to quickly get to the important stuff is kind of a thing that we advocate a lot. So what can we do? So what we do about this is utilize extracts, which we call, they're physics-based subsets of the whole calculation. So kind of on the HPC side, you run a batch job that as the solver finishes, you extract the parts of the problem that are meaningful to you. So if it's a gas turbine, maybe you have mixing planes and the blade surfaces, the hub and the shroud. Maybe there's some meridional cuts or something like that. But that represents a very small amount of the data. So what people typically do when they look at CFD is they read that data in, take a long time to read it, and they create these things and then try to make some movies or whatever, or use a script to do all that. So what we do is we save that into an extract database. And the extract database has full physical fidelity of the CFD mesh and the results. You can store all your variables on there and all the mesh geometry and stuff. And then later, you can bring that over and make movies or do whatever you want. So that's how that aircraft carrier landing was done. They did the extract processing in Maui and only brought the XDBs to Pax River in Maryland to do the actual movie production. And what's cool is because they're full 3D, you're really working with the full geometry. It's not like a movie. It's not like something fixed and still. And because there's numerical results, you can calculate lift and drag and mass flow. You go one step further, and you instrument a solver code to directly create the extracts. So this is something that's been around for quite a while, this idea of in situ processing, where you essentially, in the memory space of the solver code, you extract the important bits. So we've done this for Fluent. Fluent's current version is actually able to output these XDBs. And we've done it a lot for people who have in-house codes at gas turbine manufacturers, things I can mention, aerospace companies in Japan, NASA and JAXA. And the idea is that you reduce the number of volume files you have to save. So you get around the disk problem by simply not creating a mess for yourself. These extracts can be 1,000 times smaller than the volume file. So it's pretty cool. So these subsets, these extracts exist on a spectrum. And for example, you can, a number in a log file is a type of extract, right? If your solver writes out at the end that the top radiator temperature is 200 degrees, that's all you want, then you have a data point, right? Most people generate images and movies, but these extracts, these 3D surfaces with numerical data, they allow you to do a lot more, and those are the things that we save and we archive for data analytics. So it allows us to store a lot more of it, and because it's full numerical precision, there's nothing less than having the full problem, and essentially, we've reduced the 3D CFD problem to a topologically 2D problem, which makes it more tractable for matrix methods and neural networks and things like that. And our products actually allow you to write those extracts, and then we have these lightweight free viewers that movie was made with a free viewer, the movie of the aircraft landing. And so you can share those things around inside your company. So you can see a lot of the things that we do is now going beyond just reading the data and visualizing, but helping people be effective with this bigger and bigger data. So this was a success slide we made for Department of Energy. That's an extract. So that's that truck can be taken apart. You can do forces and moments on any part of it. It was a 100-fold decrease in data size from an unsteady calculation, and we did this with Fluent. So it's integrated in Fluent. If anybody buys Fluent, there's an XDB output directly for that code. So two other things that we're working on. I'm not going to go into detail on this, but Snapshot is an automatic, scalable validation and verification tool. You have 1,000 simulations of a wing, and you just want to know in sorted order which one have the best ratio of lift and drag. So you go into this Python interface and say go, it launches batch jobs, reads the files, extracts everything, generates a PDF report. That's currently in use at the nuclear navy where they do reactors and they can't afford to make a mistake. So they basically run 10 calculations for every one that a normal company would run. Spector is really interesting. I picked that name, by the way, because of James Bond movie, right, and Dr. No and all that kind of stuff. Not because it's anything bad. This is an automated web-based tool for uncertainty quantification, CFD. So you basically build a couple of meshes, and you set your boundary conditions not by numbers, but by probability density functions. So you say, my inlet is 10 meters per second, but it has this standard deviation. It then automatically generates, using design of experiments technology, the solver input decks, runs all the jobs, brings everything back together using XDBs into a database, and then does a final analysis to analyze the uncertainty of your solutions. Both grid uncertainty, model form uncertainty, the whole 9 yards. This was funded by Department of Energy on an SBIR. We worked with Sandia on this project. And you can't really see it in the fuzzy picture up above, but this is this velocity magnitude going vertical to the wing. So it's 0 at the wing, you know, and it increases with the typical curve going up, that black line. And there's little red smears. And those red smears are areas where the uncertainty is higher because of the turbulence model transition. It's very interesting stuff. Automated. Our idea is that engineers will, in the future, if they have to get a 90% confidence interval, they're going to have an easy way to do this kind of stuff without manually writing Python scripts and everything. So this is kind of a cool thing. We're just starting to launch this now. So this is an example. I'm not going to talk about the underlying CFD in physics, but essentially when you have uncertainty, you essentially have uncertainty in your solution from many different causes. So if you don't have error bars, when somebody shows you a plot of, hey, I matched these results, and there's no error bars, then they haven't really done the uncertainty analysis, right? Because there's all different forms, discretization, numerical, model form. And then the experiment itself. What are the error bars for the experiment that you're comparing against? So what this plot does, it's called a P-box plot. And it basically says, yeah, this inside line is the ideal curve, but this shows how much uncertainty there is. And you see it's more green out towards the edge of the domain. So that says that that's the model form uncertainty is greater. When you get near the top of the curve there, the input uncertainty, meaning the boundary conditions, are more uncertain. So you can use that to adjust your simulation methodology and get more accurate results. So now let's talk about data science. This is one of my favorite roadmaps. So today, most everything you've heard the last 2 days is on this side of the road. So you come in at the top, start. Do you have more than 50 samples? If no, get more data. I love it. It's my level here. And if you go through all this and you get down to the bottom, we have the tough luck. You're out of there. This is on the internet. It's the scikit-learn, which is one of those open source Python things for machine learning. So this is everything we've heard about today about image processing and driving and everything is on this side of the chart. And we're interested on this side of the chart, which is dimensionality reduction and regression. We're interested in the mathematical side of machine learning, using eigenvalue analysis rather than training a neural, deep network to do something. So it's a completely different thing. And so the previous speaker talked about the really hard problem is 3D, and we have guys working on that. So all of that is on the right side. So that's the kind of stuff that we're working on. So we look at this as kind of a matrix, right? That machine learning, like neural networks and stuff, is here. Matrix methods, such as proper orthogonal decomposition, dynamic mode decomposition are in the middle. Signal processing, FFT, and wavelets is on the top. And basically, the more you know about your problem space, the farther up this bar you could go. So when you're training a neural network, you're basically saying, I got a bunch of images, and I want 10 possible outcomes. Go to town. And it calculates gradients and builds up matrices and all this. It's interesting. It's linear algebra inside there too. But builds up matrices, does evaluation, and you end up with a matrix of weights and a vector of biases, and your machine is trained. What we're interested in is this idea of using matrix methods both for surrogate models and for understanding. If we can essentially create a signature of unsteady CFD solutions and post-process in this signature domain of the prioritized eigenvalues or dynamic modes, for example, you're looking at problems in a completely different way. You're not thinking of a cutting plane and an isosurface of pressure. You're thinking of persistent, dominant, high-energy features and how they impact each other in the flow field. So what we bring to the table in terms of data science is understanding the CFD, the math part of CFD, fluid mechanics, and getting that into the matrix systems. And it's not easy. It's not trivial. It is definitely not trivial. This very simple thing, I like a simple picture. Getting data into analysis, right? So you have row space and column space. So you have an unsteady calculation. Every time step is a column. And every row is a node. So if you've got a billion cell calculation in 3D, you need a billion rows. That's definitely a problem for HPC. So a billion rows and 1,000 time steps, that is a huge parallel matrix solve problem. That's what's interesting stuff for us. So just like in machine learning, you do simplification such as convolution up front or eigenvalue analysis up front in order to simplify things going into the neural network. There are many types of tricks and techniques to use here. For example, if you're doing proper orthogonal decomposition, you can do it separately on each of the parallel domains and then combine them together using an iterative technique called hierarchical pod. There's spectral pod. There's all these different, this is a super hot research area right now in terms of data science stuff. So whereas machine learning is way out there, people are using it, they're making cars and all this stuff. The math of doing this kind of stuff, the eigenvalue analysis, is really still in the research stage. Very interesting. And there's a representation of CFD in dynamical systems that is just amazing simple. If you imagine you have a car, full car with the engine going and everything, and you have 10 billion points, and you have pressure at each of those 10 billion points. That's a vector with 10 billion elements. So in 10 billion degree space, that is 1 point. And as that car is driving down the road, that 1 point is moving on the surface of a manifold in this high order space. And this guy, in 1931, this guy named Koopman, figured out this thing called the Koopman operator to say, how can you go from a high order space to an infinite dimensional space? He enabled all these magical transforms. And this is just such an exciting area where we're taking stuff from like the 1800s and the beginning of the 1900s and putting it on computers and doing magical stuff with it. It's pretty amazing. So here's some actual examples. This was the AFRL project I mentioned. This is to understand design space, where I have a full 3D unsteady machine, and I'm trying to optimize to reduce compressor stall. Compressor stall is a bad thing, and it's a 3D effect. It's like a bubble gets sucked into the engine, and then bad things happen. So how can you possibly, as a human being, understand 10 different designs when it's this giant, complex 3D machine with things rotating around and everything? So what we did was we used reduced order models to study radial plots of constant radius, and reduce their complexity by using just simple single value decomposition. We're able to, this is the original data on the original plot. This is a reconstruction using 1/100th of the modes. And it's within just, I think, 1% in terms of the total energy difference. So you get, if you think about the XDBs I was talking about before, now we apply reduced order analysis to the XDBs to further reduce things. The other thing that comes out of it is feature detection. The modes tell you something. And I won't get into it right now, except that the location of shocks is really important. And you can get the location of shocks by arithmetic on the modes. It's pretty amazing. So that whole giant 3D machine can be broken down to a 2D problem in linear math. Things can get more complex. This is dynamic mode decomposition. So this is a cross-flow jet, the red thing. And you take that data, you put it into a matrix, you do dynamic mode decomposition, and you essentially get eigenvalues of frequency, which you can then reproject into the CFD space. And so this is the physical energy corresponding to this frequency. And so you can start to understand complex 3D machines in other spaces. Very important stuff. So what we do in our FieldView product is we allow you to take CFD from test data, from XDBs, from Solver, from Fluent, OpenFOAM, all kinds of different codes, and go directly to the open source tools we're talking about today, MATLAB, Octave. We actually ship a version of Octave with FieldView for free because we want engineers to start playing with this stuff because it's very, very interesting stuff. So instead of being an endpoint, it's a waypoint now in terms of data science. So I'm going to jump ahead as I'm running out of time. Here's a kind of an example. This was a simple airfoil, 2D airfoil. Ran a bunch of different Mach number, Reynolds number, angle of attack. And what you get out is drag, lift, and moment. It's just a cloud in space. Throw that into a matrix, I'm ready to rock. And you'll see, out of that cloud of miasma comes the fact that the lift is linear with respect to Mach number. Aerodynamicists know that as a fact. The machine didn't know anything, but it's telling you that fact right there. It's pretty amazing to me. So coming back to this is what we think we want to be able to do, right? Is to take a Formula One team, does 100 changes a week, take all that data, mine it, and be able to tell them that of all those changes you're making, these are ones that made a difference for you. Don't even bother with these. They're losers. And it's all about building a better numerical conceptual model. So that's it for me. I'm just about done. I went over a little bit. But thank you again very much for your time today. And I'm very grateful everybody came before me because I wouldn't have been able to do this in this time. Thank you. Questions? If they're hard, I'm going to direct them to the Ford guy. Uh-oh.
So I owe you an apology because I should have given you this information sooner. So Steve had a chart that talked about the holy grail of certification by simulation. Just to pour a bucket of gasoline on that fire, it takes 5 airframes a year to go through the certification process. One of them is a structural test vehicle that's usually stressed until the wing breaks. The other 4 are involved in flight testing for handling qualities and stall speeds and ETOPS and all that stuff. But it's a 1-year delay in starting that revenue income stream. So you're sitting on all this expense and no money coming in. And it's 4 airplanes that are tied up for a year. It's a huge value if you can get there, and they will.
Yeah, I think the auto industry now is WTLP, right? That's a sort of a simulate to certify thing for fuel economy. And uncertainty is just a big bugaboo for that. So, more questions? All right, guys, thank you very much.
Steve, thank you.